Hypothesis testing. Typically, we have conjecture about the parameters we want to estimate from data. For example, when we are looking at how household income affect food consumption expenditure. So we regress household food consumption expenditure against household income using ordinary least square estimators. So before running the regression, economic theory would suggest that income positively affect food expenditure. Food is we call this food is normal goods, or in other words, beta 2. So remember, we have yi is equal to beta 1 plus beta 2 xi plus error term I. So this beta 2, we know it should be, we expect beta 2 should be positive. So after we run the regression, we can test whether this is the case or not. So what is hypothesis testing? Hypothesis testing procedures compare a conjecture we have about a population to the information, so about a population, okay, to the information contained in the data, in the sample that we have. So given an economic and statistical models, hypotheses are formed about this economic behavior. These hypotheses are then represented as statements about the model parameters. Okay, for example, we might want to check that beta 2 is equal to 0 or not. And hypothesis tests use the information about a parameter that is contained in the sample data. Is least squares point estimate, is standard error, and draw the conclusion about the hypothesis, whether we want to make a decision whether we want to reject or we fail to reject the hypothesis. So hypothesis test contains these 5 elements. First, we need to have a null hypothesis. And generally, we are going to maintain that this null hypothesis is true unless we have evidence against it. And corresponding to a null hypothesis, we have what is called alternative hypothesis. So if the null hypothesis, if we reject a null hypothesis, then we are going to accept the alternative one. And given this null hypothesis, we then develop what is called test statistics, which is a random variable, which is going to be a function of data and is a random variable. And we choose what is called alpha level of significance, then decide a rejection region. So we are making a rules. We are setting up rules for making the decisions. Then we reach a conclusion. Okay, that's 5 elements we typically have in the hypothesis testing. Okay, let's look at these elements one by one. A null hypothesis. It is the belief we will maintain until we are convinced by the sample evidence that it is not true, in which case we will reject the null hypothesis. Typically, it's stated as this. H0 is beta k. For example, in our food expenditure example, would be maybe H0 is beta 2. Let's check the second parameter is equal to C. We want to check whether it's 0 or not. So note that this is how we write out the null hypothesis. We cannot write it as, say, like this. H naught is B2. Remember, B2 is estimate, point estimate of beta 2 is equal to 0. This is wrong. Okay. We want to check whether the true value of the second parameter that we want to estimate is equal to 0 or equal to C, any C. Paired, so that's the null hypothesis. Then paired with every null hypothesis, there's a logical alternative hypothesis, H1, which we will accept if we reject the null hypothesis. So here the alternative hypothesis is flexible and somewhat depends on economic theory. Okay. For example, for our food expenditure, then H naught is beta 2 is equal to 0. And we have economic theory suggests that beta 2 should be positive. So alternative hypothesis would be beta 2 is positive. That's one alternative we can test. Alternative hypothesis we can have for the corresponding null hypothesis. So there could be three types here. So H naught is beta k is equal to C. One is right tail. Beta k is positive. It is bigger than C. Left tail, beta k is less than C. Or two tail, beta k is not equal to C. Okay, so now we have null hypothesis, alternative hypothesis. Then we can construct a test statistics, which will depend on data and random variable. And particularly, these test statistics need to have a known probability distributions. So the distribution of these test statistics should not have any parameters that we don't know it, and should not depend on data. It has some other. It should have a different distribution if the null hypothesis is not true. Okay, and for our when we are testing the parameter of regression models, the test statistic is like this. So T is equal to BK, the OLS estimate of beta k, minus C, which is remember under the null hypothesis, we know that we see that beta k is equal to C. So we take away C, so remember we have this. If you remember previously, we can normalize, we can standardize BK, and this way BK minus beta k, which is a true value. BK is the estimator of beta k, and we know that beta k has an expectation of BK has expectation of beta k divided by standard deviation of beta k. Okay, so under the null, this beta k is equal to C. So let's replace beta k by C. And the standard deviation of beta k, typically we don't know that. So we need to estimate. So we estimate the variance of BK and put a head on top of it. To denote that is estimate. And we call this standard error of BK. And we can show that. We will not show it because somewhat is a little bit technical. So for our subject purpose, we take this as given. So we can show this test statistics is T distribution with degree of freedom n-2. Okay, and note that this distribution does not depend on any unknown parameter, does not depend on data, right? So it's good for our purpose. Okay, so from the sample, we can calculate a value for test statistics. And then we decide whether to reject the null or not to reject it. So here, heuristically, we can think. So remember our T is this. So our null hypothesis beta k is equal to C. So if our null is true, then clearly BK is the estimate of beta k, so BK should be very close to C, right? So all this T, the value of T statistic should be small, and I'm having a quotation mark here. So here I'm talking in kind of vague language. You should be wondering what does it mean by small or large. So if our null hypothesis is true, then our T value should be small. So in such case, if we compute a very large value of the T statistics, then we will reject the null because we believe it under the null it should be small, but in contrast we get a big value, so then we reject the null. And what does it mean by small, large? To be precise about this, we need two things. First, we need to choose a level of significance and set up a rejection region. So if our computed test statistical value is located in this rejection region, we are going to say we reject the null hypothesis. If it is outside this rejection region, we are going to say we fail to reject the null hypothesis. So typically, we are going to choose alpha level of significance to be either 1% or 5% or 10%. And the rejection region depends on form of the alternative. It is the range of the rejection region is the range of values of the test statistics that results in rejection of the null hypothesis. So to construct this rejection region, we need the test statistics, and importantly, its distribution should not depend on any unknown parameters. And we need to have an alternative. We need to choose alternative hypothesis. We need to choose a level of significance alpha. So the rejection region consists of values that are unlikely and that have low probability occurring when the null hypothesis is true. So the logical reasoning is, if a value of the test statistics is obtained that falls in the region of low probability, so this rejection region has a very small probability of occurring if the null hypothesis is true, then it indeed occurs because we already computed this. We computed this as the value of this statistics that falls into this rejection region. Then this event occurs. This event of small probability occurs. In these cases, we reject the null. It's unlikely that the null hypothesis is true. If the alternative hypothesis is true, then values of test statistics will tend to be unusually large or unusually small. Depending on our alternative. Okay. So our null hypothesis is this: H naught beta k is equal to C, and we believe that our theory tells us that beta k should be bigger than C. So the null hypothesis is H0 is beta, H1 is beta k bigger than C. And we calculate this T statistics bk minus C divided by standard error of bk. Okay, that's, and furthermore, this is T distributed with n minus 2 degree of freedom. So this is T distribution with n minus 2 degree of freedom. And so alternative hypothesis is beta k bigger than C. So we choose an alpha. Alpha, for example, is 0.05. We find the area, the probability that we find a TC, so that probability bigger than or equal to TC is equal to alpha. This is 5%, 0.05. And remember, this is PDF, okay? So the area, and this is TC. The area under the PDF, that's the probability. And we want this to be alpha, the corresponding TC, which is actually the percentile. We can write percentile of 1 minus alpha with degree of freedom in minus 2. Okay, and we can look for this from the statistical table or from statistical package like R. And if, so clearly this is a region, rejection region. This region bigger than TC is the rejection region. If our computed value of the statistic is bigger than this TC, then we are going to reject the null hypothesis, accept the alternative. So that's one possible alternative hypothesis. Second one is this sign. Beta k is less than C. Our theory says that beta k should be less than C. Okay. Then we look at this tail. Okay. So if our compute, but first choose a level of significance alpha, 5%, 1%, 10%. Determine the critical value. The critical value is the level of T, so that this region probability that T is less than TC is equal to alpha, this region. So now for any T value below this TC in this region, that's our rejection region. If computed T is false in here, then we will reject the null hypothesis. If this computed T is here, then we fail to reject the null hypothesis. So that's the second alternative hypothesis. So both the first one and second one, they are one tail. Okay, only one tail of the T. We are looking at the one tails of the T distribution. In contrast, if you have an alternative like this, beta H0 is beta k equal to C, H1 is beta k is not equal to C. So in such cases, now we want this, if the null is true, then beta k should be beta k, then bk minus C should be very close to 0. Shouldn't be too far away. So let's choose an alpha, say 5%. And we don't want it to be either too big or too small. So let's, and again, remember that this T distribution is symmetric. So we want to choose a TC so that this area and the middle area, which is symmetric around 0, is this area, sum up to 5%. So each part will be 1/2 alpha, which is 2.5%. 2.5%. So the rejection zone now is this area. So for all t, if falls on this region, then probability of this happening under the null is very small. It's less than 5%. Then we reject the null. If in contrast, is 4 with the computed t value is 4 within this zone, this region, it has a high probability of occurring under the null. Then we fail to reject the null. Okay, so here is the step-by-step procedures for testing hypothesis. First step, determine the null and the hypothesis. Determine the null and alternative hypothesis. Then specify the test statistics. When for our regression models, generally is a t statistics, and we need to make sure that we know the distribution of the test statistics under the null, if the null is true. Then we take a level of significance, alpha, 5% or 10% or 1%, and determine the rejection regions, like previous two-tailed test, t-test. So this shaded area is 5%, suppose alpha is 5%. Then any value bigger than this negative TC, higher than positive TC, then we reject the null hypothesis. That's the rejection region. Then calculate the sample value of test statistics to see whether it falls into this region or this region. Okay. Then state the conclusions. All right, let's look at the food consumption expenditure examples. So the null hypothesis is H0 is beta 2 equal to 0. This says that, okay, income has no effect on food expenditure. And first alternative, H1 is beta 2 positive, means that income positively affect food expenditure. And test statistic is T, which is B2, the estimate of beta 2, minus beta 2. So beta 2 now under the null is 0. It's 0. So beta 2 minus 0 is equal to beta 2. Okay, so it's this. Divided by standard error, the estimate of standard deviation of beta 2, and which is T distributed with degree of freedom n minus 2. Okay, let's choose alpha level significance to be 5%. Determine the critical value, 95% interval percentile T distribution with the degree n is 40 and minus 2 is 38 degrees of freedom. So this 1.TC is 1.686. So any value is bigger than 1.686, then we will reject the null hypothesis. So that's the rejection regions. And if T is less than 1.686, we will not reject the null hypothesis. Then from the data, we can calculate the T values. So B2 is, we estimate B2 to be 10.21. Standard error is 2.09. So the ratio then is the T value is 4.88. 4.88 is bigger than 1.686. It's somewhere here, 4.88. So indeed, the value of this t stat falls on the rejection region. So we will reject the null hypothesis, which is beta 2 is equal to 0, at the 5% significance level. That means we will accept the alternative, which is beta 2 is positive, at the 5% level of significance. So we reject the hypothesis that there is no relationship between income and food expenditure and conclude that there is a statistically significant positive relationship between household income and the food consumption expenditure. Okay. We might also want to have a, so this test is one-tail test. We might also have two-tail test. So null hypothesis is beta 2 is not equal to 0. So in such cases, the t stat is still the same, which is t distribution with degree of freedom n minus 2, if the null hypothesis is true. So we select the level of significance to be 5%. Now, because our alternative hypothesis is two tails, so we need to, oops. So -2.024, -2.024. So this area, this area is 2.5%. This area is 2.5%. So they sum up to our alpha level of significance. So the rejection zone here is, let me write here. Rejection region is -2.204, positive 2.024. So this region. So if our computed t-value falls in this region, we will reject the null hypothesis at 5%. If instead it's between -2.024 and the positive 2.024, then we fail to reject null. And we compute the t-value for the t-value. We computed it to be 4.88, and again is located in the rejection region. So we reject the null hypothesis that beta 2 is equal to 0. So we conclude that there is a statistically significant relationship between income and food expenditure. Okay, this approach to hypothesis testing is called a critical value approach. In addition, we can also have a p-value approach. So when reporting the outcome of statistical hypothesis tests, it has become standard practice to report the p-value, which is abbreviation for probability value. So the p-value here is probability of the test statistics is bigger than t0. Suppose our t0 under the null, the value of test statistic is 0.5. It's like 0.5. So probability of the associated p-value is probability of t bigger than t0. That 0.5 is this area. Okay, that's the p-value. So in such case, we can determine the outcome of the test by comparing the p-value to the chosen level of significance without looking up for or calculating critical values. And this is much more convenient. So the rule of decision rule is that if the p-value is less than the level of significance, suppose we calculate p-value is equal to 0.02, and we choose alpha is equal to 0.05, 5%, then p-value is less than 5%. Then in such cases, we reject the null hypothesis. If, in contrast, p-value is bigger than the level of significance, we do not reject the null hypothesis. Okay, this is the p-value approach. For the food consumption expenditure data, so suppose that null hypothesis H0 is beta 2 equal to 0, H1 is beta 2 bigger than 0, and our t-value is 4.88. We calculate the associated p-value, which is probability that the t-stat under the null is bigger than 4.88. We calculate to be very small, 0.0. So this says that 0.96503 times e to e minus 5. This is a scientific way of writing the number. It's just equal to 0.96503 times 10 raised to the power negative 5. So it's very small. It's less than 0.05. Then we reject the null hypothesis that beta 2 is equal to 0. Okay, we can also have what is called confidence interval approach to hypothesis testing. So we can construct, previously when we do interval estimation, we can construct the confidence intervals, right? So we can construct a confidence interval of the regression coefficient of interest. So if the value of null hypothesis falls within this confidence interval, so suppose our H0 is beta 2 is equal to 0, and our 95, and let's choose alpha is equal to 5%. Okay, and that means we can compute a 95% confidence interval. So suppose we compute it to be negative 0.5 to 2. Then now 0 falls in this interval. Then we are going to conclude that, okay, we fail to reject the null. We do not reject null. If the 95% confidence interval we compute is 0.5 to 2, then now beta 0, now 0 is outside this interval, then we reject the null hypothesis. Okay, that's hypothesis testing. So typically we're going to have, say, null hypothesis is either true or false. And when we make our decision is either reject or not reject. In such cases, we can classify, we can categorize them into 4 situations. First, if the null hypothesis is true and our decision is to reject it, then we are making error now. We call this type 1 error. The probability of this committing type 1 error is alpha. So this is our choice. Okay, we can choose alpha to be 5%. So we choose a level of alpha equal to 5%. That means that we have 5% probability of rejecting the null hypothesis when it is true, committing a type 1 error. If it is false, if the null hypothesis is false and we reject it, then we are fine. We are not making any mistake. So we are fine here. If the null hypothesis is true and we do not reject it, then we are good. We are not making any mistake. If the null hypothesis is false and then we do not reject it, then we are making error. We call this type 2 error. And typically we don't know what's the probability of making type 2 errors here. So when we are conducting hypothesis testing, we can make these two types of errors. So you want which you want to be aware. All right. Sometimes when we are doing this hypothesis testing, we want to have a test linear combinations of parameters. So for example, like this, we want to. Okay, let me give you more specific examples. So we have a parameter beta 1, beta 2 as in our food consumption expenditure examples. Let's say we want to test the combination beta 1, say 0.5 beta 1 plus 2 beta 2. So we combine these two parameters. And certainly now we have estimator, a natural estimator would be, let's call this lambda a hat. It's 0.5 B1. Remember, B1 is OLS estimator of beta 1. Plus 2 B2. B2 is the OLS, ordinary least square estimator of beta 2 of this. So the estimator of lambda is 0.5 B1 plus 0.2 B2. And we know B1 is normally distributed, B2 is normally distributed, so lambda hat, the sum of two normal random variable is still normally distributed. So mean of lambda hat is just 0.5 EB1 plus 2 EB2, which is 0.5. The mean of B1 is beta 1. The mean of B2 is beta 2. Okay, that's the mean of lambda hat. Variance of lambda hat is the variance of 0.5 B1 plus 2B2. So it's equal to, so there's a formula of doing this computation. You can check the textbook for these formulas. So it's equal to 0.2 square variance of B1, which we can estimate, okay, plus 2 to the power 2 square variance of B2, then plus 2 times 0.5 times 2 times covariance of B1 and B2. Again, we can estimate from our OLS regression. Then we can calculate this. Then we can, similarly as we do the hypothesis testing of one parameters, now we combine these two parameters into one parameter of lambda. And we can do the t-test in the same way.